In this video, we are going to extend our idea of the steady state problem, and we are going to begin to ask the question of how do we determine mathematically what's going to happen to the long run, in the long run to our population. So recall this example where we had human migration patterns. We had these rural dwellers and urban dwellers, and it was the case that every year, 5% of urban dwellers moved into a rural region and 15% of rural dwellers moved into an urban region. We started off with 100 total urban dwellers, and we wanted to figure out what's going to happen. How are these splits between the 20 and 80 going to be distributed in the long run? So what we did first was we formulated a recursive equation where we determined that to get the next number, the number of people in the rural setting and urban settings one time unit later, we had to take the current states, and we know that to get the number of rural dwellers next year, we keep 85% of the current rural dwellers, because remember 15% of them move away, so 85% of them stay, and then we're going to gain 5% of the urban dwellers who are going to become rural dwellers next year. Similarly, 15% of the rural dwellers moved into the urban setting at time n+1, and 95% of the urban dwellers remained urban dwellers at time n+1. We did a little bit of math on this and found out that we could actually express the number of people in the populations at any given time t by actually exponentiating our coefficient matrix to the t power. So if we wanted r 100 and u 100, we could raise this to the 100th power and multiply it by the initial state, which we call the direct equation. Remember, the difference here is that one of them, this guy here, we need to know the previous year's populations to get the next year's population. But here all we need to know is the initial state, and by simply exponentiating to the t power, we could figure out what the populations are at any given time without having to go year by year by year. So we kind of imagined it like this. If this represents t equals 0, and we wanted to go over here to t equals 5 and say how many people are going to be in the populations, we had to go to time 1, time 2, time 3, time 4, and only then could we get the year 5 population. This is how we would do it if we were using the recursive equation, but we also have this direct equation. And this direct equation basically says, hey, you can go from t equals 0 all the way to t equals 5 by just raising the matrix to the proper power. Now, when we started to raise these to large enough powers, to the 100th, to the 200th, we noticed that as time got larger and larger, the states got closer to 25 and 75, regardless of how many of the 100 people were initially split. So we could put all 100 people at time 0 into the rural population, and still, over the long haul, there'll be a 25-75 split. The question that we might have is, how do we determine this steady state mathematically? So we define a steady state to be a state in which things are no longer changing. So if we found out that at, let's say, we looked at time and we looked at the population at that time, and we found out that, let's say around time 100, which I think we did observe, we were pretty close to 25-75. If we went one more year beyond that to time 101, we would still be at 25-75. And at time 102, we would still be at 25-75. So this is how we're going to define this thing called a steady state. It means the state of the division of populations is no longer changing. Now, there's still people migrating back and forth, but those sizes remain the same because the number of people leaving one state is the same as the number of people entering that state. So we notice that these two states that we have here, because people are transitioning back and forth every year, this is still happening, this loop, but eventually the number of people entering the urban state equals the number of people exiting the urban state, and vice versa. So how do we determine the steady state? Well, it's helpful to kind of think about this notion of there not being any more change when we've reached the steady state. So we observe that a steady state is reached when, after one more additional time unit, the populations no longer change, or at least they change by very little, because we never quite get to exactly 2575, but we get really, really close. So to mathematize this, what we're saying is that the current state and the next year's state are going to be equal to each other if we are in a steady state. So suppose that we are in a steady state, then the populations now are going to be equal to the populations next year. Well, that's good because mathematically that means that if these two are equal, I could substitute both of these vectors with the same values. So what this mathematical relationship here means that the vector at the next time, n plus 1, equals the current state, n. We can thus replace both of these vectors with the constants r and u, and we can solve for this vector. So let's call this vector right here, this is the steady state vector. We don't know what's in it yet. Well, I mean, we figured out that that's going to be 2575, but how would we figure that out without just having to raise our A matrix to large enough powers? So the way we could do that is we start off with our equations and say, okay, so if Rn plus 1, Un plus 1, to get those states, we have to take our A matrix. So there's our A matrix, it's our transition matrix, as we've been calling it. And we know that this is the general recursive relationship, but if these are both the same after some point in time, then what we could say is that in a steady state, this vector right here will replace with the constants that represent our steady state. And we know that if we were to take our current state, which is the Rn Un, then if we are in a steady state, then the number of people now, even after we transition it one more year, is going to equal the same thing. And so this makes it convenient to where we can now solve, because we only have we can form a system of equations with only 2 unknowns, whereas this one right here has 4 unknowns. The R value now and the R value next year, the U value now and the U value next year. Again, if we're in a steady state, then that means the R value now is going to be the same as the R value next time unit, and the U value now is going to equal the same value as the U value next time unit. So let's put some symbols in here and use some of our vector algebra. We called this right here x sub n plus 1. But since these are both the same, we're just going to refer to them as x, and we're going to try to solve for x. So really we have this equation that we want to solve for x. And we want to isolate x, get it by itself so that we can solve for it. So if I actually, let me rearrange this equation and write this as ax equals x. That's the same thing, I've just moved the, if they're equal one way, they're equal the other way. So what I'm going to do next is I am going to subtract x from both sides, and that gives me ax minus x equals the 0 vector. So remember, when we subtract x from itself, we don't get 0, we don't get the number 0, we get the vector 0. And now we want to solve for x. But before I factor this x out, I can't just factor it out and say this is equal to a minus 1 times x, because the number 1 is a scalar, but the matrix A is a 2 by 2 matrix, so that's not quite going to work. So how do I deal with that? Well, one convenient way to deal with that is to say, rather than to think about this as the number 1, if I multiply a vector by the identity matrix, so this is the 2 by 2 identity matrix and the 2 by 2 A matrix, and I right factor the x vector out, then I have A minus I. So that is our A matrix minus the identity matrix in parentheses. And I want that to equal the 0 vector. So let's do off to the side, let's figure out what A minus I is. So A minus I, before I plug in what A minus I is, I've got to calculate it. My A matrix is the one from above. And now I'm going to subtract the identity matrix from it, which is the 1, 0, 0, 1 matrix. So what that's going to give me is 0.85 minus 1 is negative 0.15. 0.05 minus 0 is 0.05. And then I'll have 0.15 and negative 0.05. Now, one interesting feature that you'll see here is you'll see that these two rows are negative multiples of each other. So this matrix is going to be linearly dependent. The columns of this matrix are going to be linearly dependent. Linearly dependent matrix. And so as a result, I'm either going to end up with 0 or infinitely many solutions. We'll deal with this in the next video in terms of why we're going to end up with this. But for now, we just want to figure out what this steady state is going to be. So A minus I is the matrix that we've just calculated, this one here. And inside of the x vector, we just have our two, what our steady state is, our rural population and urban population, and that has to equal the 0 vector. So I've got a perfect system of equations here. I can now solve this by doing Gaussian elimination. So negative 0.15, 0.05, 0.15 and negative 0.05, and then augment it with the 0, 0 vector, and then perform reduced row echelon form on this. What I'm going to end up with, once I plug this into my calculators, I'll have a row of zeros down here, which already is going to tell us that we're going to have infinitely many solutions, and this one up here is going to reduce to 1, negative 1/3, 0. And again, this is our R coefficient, our U coefficient, and our constants. And what this tells me is I have this system of two equations tells me that 1R minus 1/3 U has to equal 0, and that 0 equals 0. Since I don't have any information about what U has to be, this says R is going to equal 1/3 of U. This tells me that U is a free variable. So my final solution is going to look a bit like this. My RU vector is going to be, well, if I let U equal C, some constant, then U is going to be equal to C. R is going to be equal to 1/3 of C. Now this should make sense right now because if this value is 1/3 of this value, and we've already determined that our steady state based on an initial population of 100 people, 1/3 of 75 is actually 25. And that works out perfectly because we know that this value is going to end up being 1/3 of this value here. So how do we get the 25 and 75? Well, we need one more constraint to help us find a unique solution. So we know that R plus U equals 100 at any given time, since we always have a population of 100 people. So if that's true, and if R is equal to 1/3 of C, that means 1/3 of C plus the U value, which is C, has to equal 100. And so 1/3 plus 3/3 C is 4/3 C, and we can solve for C now. And that tells me that C is going to equal 3/4 of 100, which is 75. And that already gives me a unique solution, which tells me that R, the RU vector for my particular steady state, is going to be 1/3 of 75, which is 25, and C, which is 75, and we now have our steady state found mathematically without having to try to guess and check it. In the ensuing videos, we're going to actually learn that what this vector is called. It's called an eigenvector, and there's a scalar associated with this eigenvector called an eigenvalue.